Here's a good problem for practicing that long time, short time behavior of a circuit. Let's see. So consider a capacitor being charged by a battery in a simple RC circuit. So you'd want to draw that. EMF there. You might put a switch in it if you want to think about controlling the time. Simple RC series circuit. You got a resistor, you got a capacitor, and a switch. This is the kind of circuit that we solved the differential equation for. So we already thought about how does the charge and the current behave. You may recall something like this. The charge on the capacitor at time 0 is 0. We're saying it's initially uncharged, and then we charge it up. So it goes something that looks kind of like that. And that's the formula for that. If you look, the charge as a function of time is whatever it's going to get to minus, it's going to be this exponential equation like that. Whatever charge it's going to build up to, which is just the EMF times the capacitance, 1 minus e to the minus t over RC. RC is that time constant. We could think about discharging, but this problem is just about charging, I think. You could also take the derivative of that to get the current. So the current kind of does the opposite. At the beginning, the current is high. There's no charge on the capacitor, but current or charge flows immediately onto the capacitor because it doesn't have any potential drop yet. All the potential is across the resistor. So you start out with a lot of current, and then it goes down like that towards 0. Because once it's charged up, you get no current anymore. So the formula for that then, the current as a function of time, is whatever you start at, e to the minus t over RC. Or in this case, that I naught would be what? At the very beginning, it would be the EMF over R. Because at the beginning, nothing's happening here. So I naught is the EMF over R. And here, Q naught, what it's going to build up to is to the point where the whole EMF is over C. So it is Q naught is E times C. So you probably don't prepare that much before you read the answers, but anyway, that's what I'm doing because I'm kind of lecturing. Now let's read the questions. After a switch is thrown to charge the capacitor, when is the battery delivering the most power? The capacitor is fully charged, it's half charged, immediately after the switch is thrown, or the power is constant. So there's a little bit of a tricky thing. We talked about the power dissipated in a resistor. We talked about the energy held in a capacitor, but power from a battery, well, you just got to know that that's the same as asking the power dissipated from the resistor. P, the formula you're used to thinking of, P is I delta V. That's sort of the power dissipated in a resistor when you're considering the voltage across the resistor. But through the same ideas, it's really just pushing charge. How fast are you pushing charge across a potential? That's what the battery is doing. It's taking charge and building it up to a potential difference of the EMF. So for a battery, the power given out by a battery is just I times the EMF. I drew those as big I's, implying they're constant, how we usually think about it, but you can just put in the little I and see how the power changes in time. So according to that, after the switch is thrown, charge capacitor, when is the battery delivering the most power? Well, constant, varying in time. When is I the highest? Yeah, time equals 0. These are both time, by the way. So as soon as you close it, you have the biggest sort of jump, the biggest current right when you close it. Because there's no EMF, there's no voltage drop. None of the EMF of the battery is being taken up by the capacitor. It's all over the resistor. So V equals IR. That gives you the most current. So anyway, yeah, so it's multiple choice, but it's the one immediately after the switch is thrown. Question 2. After a switch is thrown to charge the capacitor, when is the electric field greatest in the capacitor gap? Aha, tricky question. So similar choices, fully charged, half charged, right after you throw the switch, yada, yada, yada. So the field in the gap between the capacitor, so you want to say, what is the field in a capacitor? We actually have sort of two equations for it. We have that it could be the charge density on the plates over the permittivity of free space. That's one thing it could be. Charge density of the plates, remember that's Q over A, so the charge on the plates over the EMF, or the E naught. So you look at that and say, well, okay, that's when the charge is biggest, right? The charge is biggest when? At a long time. So the answer to that one is once the capacitor is fully charged is one of the choices. So the biggest charge gives you the biggest charge density, gives you the biggest E. Question 3, after a switch is thrown to charge the capacitor, when is the capacitance the greatest? And standard things, fully charged, half charged, immediately after the switch is thrown, or the fourth choice is the capacitance is constant. And the answer to that one is the capacitance is constant. The capacitance doesn't care at all what currents and charges and potential differences and switches, what anything is doing. The capacitance is strictly a function of the geometry and the construction of that capacitor. Epsilon naught A over D, and if there's a dielectric in there, slap on a K. If it's just air or vacuum in the gap, then that's just 1. So that's why that one is independent, constant.